Hello, welcome to the Useless Stuff Shop. I'm Bort. Today's video is about adding heat to a 3D printer's enclosure. Thank you for joining me. The objective today is to add heat to the 3D printer's enclosure. Why do we want to do that? Well, I want to get some control over the environment here. The temperature ranges between about 16 and 22 centigrade, depending on time of day, time of year, etc. And that introduces a process variable that can be a little difficult to deal with sometimes. I get good prints, but consistently getting good prints is another matter. And it's cool. So step one, define the requirements. You must heat the enclosure to a minimum of 35 centigrade. That's sort of arbitrary, but it gives some headroom above what I think is going to be necessary. It must use 110 volt mains power because that's what I have here. It needs to heat only. The temperature in here never really gets above 22 centigrade, so there's no need for any cooling. And I need to be able to control the temperature to at least, or at most, plus or minus 2 degrees centigrade. Plus or minus 1 is probably achievable, but I'll leave it at plus or minus 2 for now. Constraints. These are the limitations that I have to work around. Must use natural convection only, no fan. So you may have seen the video where I went on and on about converting my printer to liquid cooling so that I could get all the fans out of there. Why would I go and add another fan, right? I want to control the environment. I'm limited to about 600 watts of available power. The printer, its heated bed, and the central vacuum system are all in the same 20 amp circuit. And they can't all run at the same time, especially if I add another heater to it. So I'm going to put this semi-arbitrary limit of 600 watts in there, gambling that that is low enough that these things can cycle on and off and not trip the breaker in the middle of a print. I can insulate the bottom, the back side, and the top of the enclosure only, because the other sides are all necessary for access. It must fit within the printer's enclosure. I don't want anything hanging around on the outside. It has to be safe and not present a fire hazard or a personal injury hazard. It has to not interfere with the printer's operation. The temperature control is also mounted inside the enclosure, and there's an important aspect of that I'll touch on later. It can't be a radiant infrared heat source because of the tendency of those heat sources to heat other surfaces around them. That would introduce a problem. The heater and the temperature control need to be off-the-shelf components. I don't want to have to design these things. And total cost should be under $100. This is a soft requirement just to make it easier on my wallet and more accessible to viewers. The first thing I need to do is clarify the physical size constraint. That is the physical size and shape, volume of the heater and the controller that can mount within the printer's enclosure, without interfering with the movement of the print bed, without interfering with human access or presenting a burn hazard or something like that. So let's look at that first. I need to define the shape and size of the heater. I'd like to put it here at the back of the enclosure where it will interfere the least, and I need to take into account the maximum rearward excursion of the print bed. See, I don't have a whole lot of room to work with back here. All right, my actual dimensions here are 800 by 800 millimeters. I'm going to go a little smaller than that. And the thickness of this thing, this dimension, I'm going to choose an arbitrary dimension of 200 millimeters, just for giggles. This dimension is determined by the height of the print bed At 150 millimeters, I'm leaving myself a little bit of clearance. And this actual measured dimension was 90 millimeters, but I'm going to make this smaller to make sure that I don't have any pinch points between the print bed at its rearmost excursion and anything that might be back here and fingers. So I'm going to make this 75 millimeters. So this is the rough three-dimensional sketch of the volume available for a heater within the enclosure. So now we're getting to the fun part, right? Where we get to build stuff. Awesome! I looked at a number of possibilities for the heater, and the first thing that I looked at, because it's just cheap and easy, is a residential baseboard heater. Super simple to wire up, it would probably fit just fine, but I just can't see one of those things in the printer enclosure. This funky, old-ass beige contraption in there, in what is supposed to be this singularity of awesome technology. I just can't do it. So I'm forced to look at other solutions, forced by my own vanity. I'd like to try this. This is a 1000 watt, 110 volt electric heater. What I like about this heater is it's small and compact and easy to mount. However, the astute observer may note that this heater does not meet a couple of the initial requirements. One is that it is a 1000 watt heater where the maximum for this project is 600. The other is a little more subtle. If you note the fin spacing here, these fins are pretty close together, and that gives this heater a lot of surface area for heat exchange. But this is where it differs from a natural convection heater. In a natural convection heater, the fin spacing is much more wide than that. It has a lot less surface area and a lot lower power density. So this could be an interesting challenge to work around. The trouble with using a forced convection heater in a natural convection scenario is that because of the power density and because it doesn't have a fan forcing air through these fins, its ability to exchange heat to air is considerably limited. And the result of that is that when power is applied, the temperature of the heater will just rise and rise and rise and rise until we have a problem. It has a PTC thermistor type circuit breaker. However, I cannot rely on this for temperature control. This is not a thermostat. It is only intended to be a safety device. What will happen is, if I rely on this to be a thermostat, is that over time, as it cycles, its contacts open and close, they will arc. And that will very slowly erode the contacts until either one of two things happens. They either no longer make contact and the thing doesn't work at all, or they weld together, in which case we're about 2 or 3 minutes away from a fire. Either way, it doesn't work. What do we do? Well, I have an idea. Now you might ask, well, Bort, how does adding a second heater bring down the power dissipation and the total wattage? Well, it wouldn't if we were to wire them in parallel, which is the typical scenario for building wiring. However, in appliance design, engineers will often use heating elements that are arranged in a series configuration or some series parallel configuration. So if these are wired in series, one after the other, an interesting thing happens. If we visualize these heating elements as simple electrical resistances in our circuit, we have an AC voltage source. Each one of these has some resistance. Total voltage source is 110 volts AC. in a normal scenario, we have 1,000 watts running through it. However, with two of these in series, we double the resistance. And if you follow this through Ohm's law and Watt's law, what happens is the total power dissipation drops to 500 watts. And furthermore, the power dissipation in each heater drops to 250 watts. So the end result is we take the total power dissipation down by half and the power dissipation per heater down to 1/4 of its original number. And the hope here is that reducing that power density by 3/4 will allow us to use a forced convection heater in a natural convection scenario. Let's test it and see. Now let's run a quick test here on the bench. I have these two heaters wired in series, and on this end I've painted the surface matte black so that I can measure with a non-contact infrared thermometer. Plug these things in here and we'll see what happens. I'll get a quick initial temperature. You read that? 17.3. See what happens here. And there we have it. Did you hear that little click? The PTC thermistor just popped open. So this is a bust. The power density is still too high to use these in a natural convection use case. One of the things that you get with my projects is you get to see me change clothes a lot, because sometimes I only have a few minutes here and there to work on them. Another thing you get is you get to see the whole project, warts and all, because I think that it is just as important to show the things that don't work as the things that do work. These heaters didn't work. Even at 1/4 their original power density, the power density is still too high and the heat exchange is still too low for natural convection only. Kind of a bummer, but that's why we test, right? Plan C. Must be a convection only heater. I can't push that boundary apparently. So, I recently discovered ceramic panel heaters. They're pretty uncommon in my part of the world. Maybe you've heard of them before, but I hadn't discovered them until just recently. This heater is about 24 inches square, about a ½ inch thick. It is a 400 watt wall heater. Runs on 110 volt AC. It has a power switch, on-off switch, but no temperature control. It was supposed to come with one and didn't, but I would replace it anyway, so I'm not going to make a big deal out of it. It also comes with this self-adhesive heat shield, which would go on the wall. And I'm going to use this because this panel is going to mount to 1/8 inch acrylic, which is both kind of thin and fragile and heat sensitive, so I'll definitely need this. It also includes some mounting hardware, some screws, and a couple of different kinds of drywall anchors. I won't be able to use these because I'm not mounting it to drywall. The way that this heater is intended to mount is on these little standoffs, plastic standoffs, with a screw cap to hold it on, and this wood screw through it and into a drywall anchor. I'm going to forego most of that noise. Going to use a 1.25" lag screw, 1/4 by 1.25", two 1/4 by 3/4 rubber backed fender washers. Put one on the screw like this. I'll run the screw through a drilled hole in the acrylic. Put the other rubber backed washer on the inside of the enclosure so that the rubber washers sandwich the acrylic material, so I'm much less likely to crack it. And then this 1/4" thread will screw right into this plastic material. It will be a good firm fit. For this project, temperature controller selection is just as important as any other component. The controller needs to run on US AC mains, needs to be able to switch a US AC mains load of 400 watts, and needs to be economical. This little controller meets all of those requirements, and at $15 US with its own temperature sensor, it's a pretty economical choice as well. Now that the heater and the temperature controller are nailed down, I'm done with component selection, I'm done with the research portion of the project. The first thing I need to do is design an enclosure for the controller. You need a cute little box to mount the thing in that allows wire egress in the back. So I'll see you in a couple weeks, I guess, however long it takes me to make it. Here is the completed enclosure for the temperature controller. Printed of 2 pieces of nylon. They screw together with 2 little 440 machine screws. These probably aren't the best screws for this, but I just happen to have some sick-ass billet titanium screws that I got at an estate sale years and years ago, so I use these, but you could use metric screws, and M3 would probably fit too. Just drill and tap as you need. And I'll put these models up on Thingiverse with a link in the comments. It mounts the temperature control like this. Right there. Wires enter through the rear. Now it's time to test. The first test we should do before getting really carried away with this is just to make sure that this thing will respond to a temperature input. It's showing us the ambient temperature in here now. I'll set this for something just a little over that. Say 20 degrees. The heat circuit is on right now, so it believes it's heating. So if I hold this temperature sensor, there we go, it just turned off. The response is pretty slow, but it is cooling off again. When it gets a little bit below the set point, it should turn the heat circuit on again. I should point out that this kind of temperature controller is not a PID controller, so it does not try to maintain a set point temperature with a high degree of precision. Instead, it uses hysteresis, and it'll have a degree or more on either side of the set point at which it will turn on and off, and that prevents it from oscillating. And that level of temperature regulation will be good enough for this application. Alright, just turned on again. So this much works. Now that we have a reassurance that the system is at least reasonably safe, we can proceed with a more thorough functional test. I have closed the temperature control loop by taping the thermocouple to the surface of the heater. Turn the heater on, and I'll now reset this temperature to 30 degrees, a set point that is above ambient, but not so far above that it will take a long time to reach. Alright, heater circuit is on. There we go, turned off. So we got up the temperature. Feels a bit warmer than 30 to me, but this thermocouple is a little slow to respond. I'd call this a successful test, so I think we're ready to install now. You know, I really dislike it when stuff gets in the way of a good time, like practicality and common sense and BS noise like that. But in this case, I think the end result will be better if I just stop and think about this a little bit. If I can do some of the wiring here on the bench, I can save myself a bunch of headache when I try to install it. What I'd like to do is pre-wire this temperature control. Something like this. AC line wires come in here to these two terminals. The thermistor wires connect here to these two terminals. And the load relay is these two terminals over here. I'll ignore those two terminals on the far right because they are for a cooling function that is not used. To pre-wire this, I want to connect wires to these terminals, pass them back out through the holes in the rear of the enclosure to these connectors. These connectors are kind of interesting. Just crimp the wire in like that and close it when you're done, and then you get a similar connector with wires in it, and they will just snap together. Easy peasy, right? So I'll keep the high voltage stuff, the line and the load over here on this connector, and a low voltage thermistor on this connector. Building stuff. Oh yeah, giddy up. The idea is that this temperature sensor will go on the wall right over here. So it's about midway between top and bottom, and will hopefully pick up roughly the average temperature inside the enclosure. And now I will use this ultra high-tech carbon fiber pointing device to show you what I've done, hopefully without blocking the view with my own body like I usually do. Up here we have the thermistor mounted a little higher than what I had originally intended. I didn't have quite as much cable as I thought to wrap all the way around the back of the enclosure and out here. I didn't plan every little detail. Maybe I should have. The controller in its little box is right here on top of the very similar controller for the heat bed. This is a Keenovo 1300 watt AC mains per bed heater. The wiring runs back to the back corner of the enclosure where it exits through a brush grommet. Here you can see the mounting of the heater It's 4 mounts that go through the back wall of the enclosure, and the brush grommet that I was talking about is right back here, conveniently placed, almost like I had thought about it ahead of time, but it is actually just a convenient coincidence. So I should probably test this and see if it actually works. What do you think? It reads ambient of 17.8. I'll set it for 25 and see if it can get the enclosure up to 25. I don't have the insulation on yet. It took about half an hour to get up to 25 centigrade. In that time I've needed to go ahead and start a print so I can take advantage of the overnight print time. This looks like it is going to work out pretty well. I don't yet have a feel for what its maximum temperature limit will be, but if it can keep the enclosure up to 25 without any insulation, I think that's pretty good. I think that's all I can get to for right now. I might be able to do some insulating on the bottom, but I'd be disturbing the print to do that. And it would be really tough to do because the printer sits on a 90-pound slab of steel. There's a 1/2 inch thick slab of steel under there to try to minimize ringing. It's not easy to move. Alright, it's 24 hours later, my print is done. It's time to give this thing a proper test. I want to see how hot it gets. I want to take it up to 45 if it'll get there. I don't want to go any higher than that because there are PLA parts inside there, and the heat deflection temperature of PLA is somewhere around 50 centigrade, I think. I'll try for 45 and see how it goes. You know, overall, I think that went pretty well. The thing can probably reach the target of 35°C at the print bed if I wanted to wait a little bit longer, but the big steel plate in there is a huge thermal mass and it takes forever for that thing to change temperature. And I was probably fighting that. I waited for a few hours and it was just excruciatingly slow. The temperature sensor needs to be relocated from its current location down to the level of the print bed. I should have anticipated that. In hindsight, it seems kind of obvious. That'll skew the results some. I definitely won't get up to 45-ish on the temperature controller readout at that point. There's a large temperature gradient in the enclosure. As I said, I knew that there would be some, but that surprised me a little bit without air circulation. And as long as I keep the requirement of no fan, I'll have to live with that. Maybe I'll revisit that at some point, but not for now. The goals for the project are pretty ambitious, and to come like this close to meeting all of them, that's a pretty good result, I think. I'm pretty happy with that. Didn't quite meet the maximum temperature. In my line of work, probably met the requirement is the same as not meeting the requirement, so I can't really claim it. And I blew the cost target by about 40%. The cost target was $100 US, in total it was about 140. Overall, as I said, pretty happy with the result. Well, it's been another fun project. Thanks for chilling with me. If you like what you see, please like, subscribe, leave me some comments. That's the only feedback I really get on what people think about what I'm doing. If you have constructive feedback, please let me know. I'd like to hear about it. Take it easy.